All right, so I just wanted to add a supplemental video that demonstrates how you can go about doing some of the computations of derivatives if you're trying to use the limit definition of the derivative. So there are, I'll just run through a pair of computations that will hopefully be instructive and help you out with a couple of the written homework problems for this week. So the first example that I want to do, once I find my purple pen, because all of these are examples. Example 1. So let's compute the derivative of f of x equals, and we'll do 1 over x squared using the definition, that is the limit definition of the derivative. Okay, so if I want to compute this definition, or compute this derivative, let's go ahead and just write down what the limit definition is. So f prime of x, this is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And in our case, let's go ahead and just put in what f of x is. It's 1 over x squared, or 1 over the square of the input. So this is the limit as h goes to 0 of 1 over x plus h, quantity squared, minus 1 over x squared divided by h. Okay, well, now what do? How do we sort of proceed with evaluating this limit? Well, what we can do is we can actually get a common denominator between these two fractions in the numerator of this bigger fraction. So what we can do is we can multiply this first fraction by x squared over x squared, and we can multiply the second fraction by x plus h squared divided by x plus h squared. So what I mean is we're going to do the limit as h goes to 0 of x squared over x squared times 1 over x plus h squared minus 1 over x squared times x plus h squared divided by x plus h squared. So all I'm doing here is just multiplying creatively by 1 and getting a common denominator in these fractions. So this simplifies to the limit as h goes to 0. When you have two fractions like this and you're multiplying them together, we multiply numerator times numerator, denominator times denominator. So this becomes x squared over x squared times x plus h squared minus x plus h squared over the same thing, x squared times x plus h squared, and then all divided by h. Okay, well, the whole point of doing this is that now these fractions can be combined. Because their denominator is the same, we can write this as the limit as h goes to 0 of x squared minus x plus h squared divided by this denominator. And then when you take a fraction and you divide it by another thing, that other thing just comes up as another term in the denominator. So this simplifies to h x squared times x plus h squared. Okay, so that's all that's happened here. We're just combining the fractions in a convenient way. And now what we're going to do is let's actually expand this second term here. So this is going to be the limit as h goes to 0 of x squared minus, and then what happens when we square out this thing? We get x squared plus 2xh plus h squared divided by the same denominator, h x squared x plus h squared. And now we distribute our negative sign. So this is the limit as h goes to 0. There's going to be an x squared minus an x squared, so that term cancels, and I'm going to be left with a minus 2xh minus h squared. And now look what happens, which is what we sort of always hope happens in these computations, is this h in the denominator here cancels with one of the factors of h in each of these two terms. So this is going to be the limit as h goes to 0 of negative 2x minus h. So this h and then one of these h's have gone away. And then the h in the denominator is gone, so I get x squared times x plus h squared. And now I have no problems with evaluating this limit by direct substitution. This is a continuous function of h, at least when h is equal to 0 or when it's around 0. So this limit is equal to, well, just plug in h equals 0. I get negative 2x in the numerator divided by x squared, and then if I just plug in 0 for h here, I get another x squared. So I'm going to get x to the 4th, and this is negative 2 divided by x to the 3rd. And we're done. That is the derivative of 1 over x squared using the limit definition. It's a little bit of a messy computation, but really all that's happening is we're just combining some fractions and then simplifying our way from there. Maybe expanding out a square or a sum of things that's being squared, but nothing more complicated than that. Okay. The second example is we're just going to do a simple polynomial. So example 2. So using the definition, compute the derivative of f of x equals, and we'll do 2x squared plus x, just to make things interesting. Okay, so where do we start? Well, we start in the exact same place. Let's write down the definition. So f prime of x, this is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And then we plug in what our f of x is. So this is equal to the limit as h goes to 0 of 2x plus h quantity squared. So I'm just taking my x plus h, plugging it in for x plus h, and then minus 2x squared plus x divided by h. And then the next step that we're going to do is kind of like in the last step, we're just going to expand out this square here. So this is 2 times x squared plus 2xh plus h squared plus x plus h. And then we'll distribute the negative here. This is minus 2x squared and minus x, all divided by h. Okay, so now let's distribute this 2 and simplify everything. So we get the limit as h goes to 0 of 2x squared plus 4xh plus 2h squared plus x plus h minus 2x squared minus x, all divided by h. And now we see what all cancels out here. So I have a 2x squared canceling with a negative 2x squared, and likewise an x canceling with a negative x. So I have a 4xh plus 2h squared plus h divided by h. And now we have, again, what we'd like to happen. We get to cancel out this h in the denominator. So this is 4x. These h's cancel. I have 2h squared, so this becomes 2h. And then this h divided by this h just becomes 1. And now I have a continuous function of h, so I substitute in h equals 0, and this is going to give me 4x plus 1. And once again, we've used the definition of the derivative to compute the derivative of a function. In the next week's lectures, we'll see how to do these derivatives much more quickly without having to do this limit process, but I do want us to get a little bit of practice with doing computations from the limit definition. Okay, I'll see you all in another lecture.